Hello and welcome to Deacon Wild's latest webinar, Beyond Cement, Seeking P&A Alternatives. My name is Owen Roll and I've put together this webinar. As many of you know, I am also responsible for producing the 12th Annual Decommissioning and Abandonment Summit in Houston next year. This is the first of several pieces of work that we'll be putting together to promote the industry and some of the key issues within it. And yeah, there's over 700 of you all signed up today, so thanks very much for the great response. And yeah, thanks in advance to all our panelists as well. Just a brief bit of housekeeping before we get going. The webinar will last about 45 to 50 minutes, and it's being recorded. There'll be full audio recordings and presentations kind of within a week or so. And yeah, you definitely have the facility as well to answer any questions. So on the right-hand side, there is a text box. You can put in any questions on there, and at the end we can try and get to as many of those questions as possible. Henry St. Alban, the VP of Advisory at OTM, who actually manages the plugging in and abandonment collaborative environment, PACE, will actually chair this conversation from here on in. So a massive thanks to Henry. And yeah, without any further ado, I'd like to pass over to him.
Thank you very much, Owen, and good morning and good afternoon to everyone, depending on where you are. Before we get going, I'd just like to quickly introduce our panelists. So we have Paul Carragher, who's the CEO of Bison, Phil Head, the founder and director at PandaSeal, and Professor Richard Nielsen, who is the Dean of Research and Knowledge Exchange at Aberdeen University. So these guys will be giving the bulk of the webinar, but before I hand over, I just thought I'd set the scene. So back in 2016, my company OTM conducted an industry survey where we asked what are the priority R&D or knowledge sharing areas for plugging and abandonment. The results are what you can hopefully see on your screen. Really the four big ones were cost-effective plugging and sealing, rigless P&A, barrier verification and multi-string logging, and novel barrier materials, which you can see highlighted. So just a little bit about PACE. It stands for Plugging and Abandonment Collaborative Environment. We started in 2016. The membership has grown pretty steadily and continues to do so. It consists of a number of operators and service providers, and really its objectives are to deliver disruptive technological change in P&A. So we've been fairly Gulf of Mexico and North Sea centric so far, but we're starting to engage with the broader P&A market, as you can see shown on this map here. And in each of our meetings, we have been addressing one of these four big topic areas. So just a quick word on what the operator members are selecting in terms of abstracts submitted for the meetings. The highest proportion of abstracts selected are indeed in new barrier materials, which from PACE's perspective tells us that this is an area seen as a great opportunity by the operators in terms of cutting costs and safely and effectively P&Aing a well. So that's all from me. At this point, I'm going to hand over to Paul from Bison. Paul, over to you.
Thank you, Henry. So, as I've said, I'm the CEO, founder of BISN, based here in Houston. We also have a facility in the UK. Today, I'm going to talk about bismuth alloys and using them downhole and our experience of using bismuth alloys. So we're not the first people to look at using bismuth alloy downhole. The Schlumberger brothers looked in the 1930s at melting this alloy. Why bismuth? Well, the main reason, it's one of the few elements that expands on solidification. Just like water, when it changes to ice, it has approximately a 3% expansion rate. It's also got viscosity very similar to water when it's in liquid form. So if there's any corrosion pits, wireline scorings, cracks or anything in the well, it will fall into those and seal them off. It's also very corrosion resistant, and we're doing a lot of work with the OGTC in the UK at the moment to prove up how corrosion resistant the alloy is. It's also a very dense alloy with an SG of 10, so 10 times denser than water. So we don't need to squeeze the alloy. All we do is let gravity do its job. So what do we do differently? Well, we're using a thermite reaction heater rather than an electrical heater. So electrical heaters are great, and that's what the majority of people have used for this in the past, for the last 80 years or so, because you can control them very easily. You can turn them up and down, turn them on or off as required. With the thermite reaction, we get an awful lot of heat. It's a non-explosive chemical reaction between iron oxide, rust, and aluminium powder. You put the two together in the right quantities, with the right grain size, etc. Heat it up to about 2000 degrees C. It starts a chemical reaction which produces liquid iron, heat, and aluminium oxide, and we use that heat to melt the alloy downhole. All sounds very simple, but it's taken us 8-9 years now to try and perfect the thermite reaction, to really control it, to give it as much control as you do with an electrical heater. And that's done in various ways by adding various other chemicals to slow it down. So we're now at a point where we've effectively got a very, very controllable thermite reaction that we can use to melt the alloy in situ downhole at any depth. The deepest well we've done to date is over 20,000 feet deep in the Gulf of Mexico. So the best way to think about this technology is a big candle. If your thermite reaction heater is your wick and your alloy is your wax, we run that big candle downhole, we start the thermite reaction, it melts the alloy, which then runs and creates a seal and basically expands on solidification. And I've got a short video that I'll play that basically will show that. So you'll see at the beginning of the video, we've got a heater sticking up, which is what's like a made grey metal pipe we've ignited. That starts to glow hot. It moves from top to bottom. As it moves top to bottom, just like a candle, it melts the alloy on the outside like wax, and you can see the alloy now starting to melt, and it trickles down and forms a base. It forms its own base, basically because it's eutectic, so it has a very sharp melting and freezing point. 1 C difference or a couple of degrees F difference in temperature becomes a liquid or a solid. As you can see, very, very quick reaction. A couple of minutes, we can now melt approximately 10,000 kilos or 20,000 pounds of this alloy in less than an hour downhole. So very simple, but very effective. So to just touch on some of the field experience that we've had, last year, in late last year, we did a job for Aker BP in the North Sea. And this was a well that they were P&Aing, and before they set our tool, they went in and perforated a shallow gas zone to actually create a leak underneath where they wanted to set our plug. They then ran in with our plug and set it, pulled it out of hole, and then one of the things they did is they ran in with a camera, and you can see the camera pictures there on the right hand side. They ran in, had a look at what the plug looked like. Did it look like the test plugs that we'd set when we were doing the testing in our workshop? And it did. Apologies for the O-ring that was there, that fell off the BOP in the hour or so between setting the plug and the camera run, and the company never actually told Aker BP that they'd dropped that O-ring down the well, so it was a little bit surprised to see that on the camera shot. Since then, it's been on long-term pressure test continually for the last 15-16 months now. They also have a memory gauge below, and they're going to retrieve that early next year to prove that there has been a gas buildup gas buildup underneath. They also did straight after setting it a 1.5 hour pressure test on it as well, and they also did the camera run. So we really have done as much as possible to verify that we've created a good seal, and that will be all confirmed next year. We are relatively new, and it's new technology, and everybody's always scared of new technology, but it is getting a bit more acceptable, and you can see there now our kind of growth of doing these runs. We're up to actually 30, because we run another one yesterday for 2019, spread across the whole globe, as well as P&A. We do intervention and completion work using this alloy to create a seal. And with that, I'll pass back to you, Henry.
Thank you very much, Paul. Very interesting presentation. So I'm sure there'll be lots of questions from listeners. We'll get to those at the end of the final presentation. So in the meantime, Phil, you're up next.
Phil, I think your audio's actually just dropped out. So if you wouldn't mind just disconnecting and redialing back in, and then we'll just Richard, actually, we'll jump straight to you and then come back to Phil at the end. So sorry, Richard, over to you.
Right, so I'm Richard Nielsen from the National Decommissioning Centre. For those of you who don't know what the National Decommissioning Centre is, it's a collaboration between the University of Aberdeen and the Oil and Gas Technology Centre in Aberdeen. We were set up in January this year. So the idea of the centre is to become a hub for research and development for decommissioning. And obviously, the university can't do all of that itself. We're a reasonable sized university, but not huge. So we're looking at how we work with other universities, institutions, and try and capitalise on those in terms of the research side of things. One of the other main aims we've got is trying to help the local supply chain in terms of developing its capabilities, particularly decommissioning, both for the UK but also internationally. When we set up the centre last year, or when we were talking about setting up the centre last year, we did some work with industry looking at what the key challenges were for industry. And this is very much UKCS based, but I'm sure a lot of this will have application elsewhere. So the key areas which came out were mature-based management, not surprisingly well decommissioning, and late life and decommissioning. And the biggest area in terms of the well side of things was one, cost reduction, because in the UK, the well side of things is about 50% of the overall decommissioning cost, partly because of two subsea wells. And particularly the big interest in barrier verification and alternative barrier materials. Obviously, for new barrier materials, we need to be able to do some realistic testing. And previous speaker talked about some of the work they've done in terms of well interventions already. But we need to be able to mimic high temperature and high pressure environments. We need to be able to have repeatable and consistent testing. We want to do some lab testing. And we want to be able to give operators confidence that the proposed solution is going to work before being deployed in the field. And that's even for the more extreme technologies. So extreme, I would talk about some of the thermite technologies which are out there, which in terms of trying to test in-house is quite challenging. So we got together, we used some stakeholder engagement mechanisms. We've got one through the Oil and Gas Technology Centre, which has got an alternative barrier materials group. And we also used Oil and Gas Technologies, Oil and Gas UK's plug-in abandonment group as well. And out of that, we got a kind of requirement for, if we're going to go build a testing chamber, is to look at something which is probably about 20-inch diameter, maximum working pressure 10,000 PSI, although there were operators pushing for much higher than that, obviously, because there are HPHT wells. And likewise, maximum working temperature 150 C. And we started off with a working fluid of water for this. We also put some stretch targets in for the feed study, and the stretch targets were primarily around temperature, so up to 200 degrees C, but also potential for working with brine, which also has some implications for materials choice. So we set that feed off earlier on this year, and we worked with a group called Apollo, who have then come up with the outcome for the feed study. And this is the initial concept. So we have in the centre there, the red item is the test chamber. so 20-inch diameter, about 10 meters long. We have on the left-hand side the grey piece beside the loading bay is kind of skid, where we can build a cartridge, slide that into the chamber, and then do the testing. The swivels we've got there are because the loading position is this horizontal position, but the actual test position is this vertical position. So we will load horizontally, then we'd put the chamber vertical, or you can see on the right-hand side there as well, there are a series of lock points. We could actually have different inclinations. So if somebody wanted to test at 45 degrees or 60 degrees, we could do that as well. So in terms of building this thing, the idea was to try and build something that was very modular, so that whether it's a bismuth alloy test or a thermite test or a resin test, a company can come in and do that, and we've got standard formed cartridge. So the idea was the red part here is the pressure chamber, the two blue parts are the end caps, and the green parts are then the locking rings which hold those end caps in place. And in the center, we've got a kind of fairly standard cartridge layout, which will allow us to have different tubing assemblies or casing assemblies, and various annulus as well. So the cartridge concept, the idea was to have some sort of standard interface to the test vessel. So we've got casing that can be welded directly onto the end interface. We've got ports for annulus return flow. We can put pressure and temperature sensing in there. The arrangement allows for quite a wide range of tubing and casings to suit the test, as long as we're within the 20-inch diameter. And at the right-hand end, then we've got bore seals, which stab intercept at both ends to hold the cartridge steady and also allow for expansion. So try to build this so it's as simple as possible. And we've got hot water jackets around the outside, which allow us to heat things up. In terms of the kind of process flow for this, we try to keep it fairly simple. So on the right-hand side, we've got the vessel. On the bottom, we've got the flow. So we've got primary flow loop of 10,000 psi, and this configuration is shown flowing through the bore. However, the valve pack that was in the drawing earlier on allows us to change that and flow through the bore and out through the annulus, or vice versa. So we've got quite a wide variety of tests we can run from this system. So we've got the swivels, which allow us to change the angle of the chamber, pump for the high pressure supply, and a thermal oil heat exchanger, which allows us to heat up the fluid which is being flowed through the system up to 150 degrees. We're aware that some of the tests we've got will probably need a gas cap to allow for some of the expansion in terms of liquids. So we've got a nitrogen input, and we've also got water input for the initial flood. And given the fact we're talking about quite high energy systems, one of the key things of this is having a high pressure relief and scrubber system, so that we're running very safely for this. So basically what we think we've got is we've defined how a test might be conducted using this kind of cartridge system, which is very flexible. We can adapt to almost any oil field equipment, not just plugs. We've got a variety of modes of operation because of the way the fluid system is set up. So we can have inflow from well or rock, and we could have flow through the annulus. We've tried to leave enough space in this to allow for slickline equipment interface to allow downhole operations. And we should be able to work with both in gas and fluids, and there's flexibility for other fluids as well. I guess that will come down to the materials we finally designed to build the system with. We can accommodate large variations in pressure and energy releases, particularly with the pressure release system we've got. And we can take casing sizes up to 18¾ So I think what we've been trying to do is kind of set up something which is going to be a fairly unique environment for fundamental research, but also a great opportunity for the developers particularly, but also the operators to use for some of these new tests and new materials. And I just want to acknowledge that this was supported by the Scottish Government through a grant from the Decommissioning Challenge Fund for this feed study. So can I pass back at this point?
Thank you very much, Richard. So do we have Phil back on the line?
Yes, we do.
Fantastic. Okay.
Hi there, my name's Philip Head from Panda Seal, and I'll just go through briefly what we're working on towards using thermite and low temperature alloys. First of all, we're looking at severing and sealing tubing using slickline And we have a system which we call Panda Block, which is basically a simple mechanical slickline tool to reduce the cost of a through tubing abandonment. So it's cost effective, simple. The tool's modular, and so we can make it contain different materials such as thermite, bismuth, and other materials. We have also another system where we're using fiber optic slickline, where that gives us additional advantages such as performing logging runs prior to using the thermite or the sealing material, so it can optimize the placement of the sealing material inside the well. It has obviously smarter tool functions. It can set the bridge plug. It can activate the initiator at will. And obviously, because we have a fiber optic cable going through the whole tool, we can monitor the thermite process in real time. One of the things we're quite conscious of as well is of controlling the initiation process of the thermite reaction. And part of our philosophy is to make that totally safe. How we're doing that is we have a thing we call Panda Safe, basically. It's a two-part initiator, and it allows us to separate the initiation in two separate runs. So we basically deploy a wet connector and have a lower half with the initiator in, and an upper half where we go and deploy into the well the initiation process. And as we land that assembly, the initiation process will start, and it's a totally safe, controlled initiation of the whole process in the well itself, and there's no possibility of anything happening, and it obviously eliminates expensive electronic hardware. That is our sort of tubing and sealing process. Then we have it working on another process where we want to sever and seal nested casing. And in here, we're deploying cartridges which have RFID tags. And the cartridge, we can deploy as many of these cartridges in the well as required. These cartridges are filled and delivered to the well site. And when we deliver them to the well site, we know exactly what's being delivered to the well site. It could be a variety of things like low temperature thermite, high temperature thermite, propellants, either solid or liquid, the initiators, bismuth, or even resins and weighting agents, and thermal insulation, which I'll come to in a second. The fact that we're using the RFID means that each of these cartridges can talk to each other, but the RFID is totally passive. The fact that we can daisy chain information in both directions means we have a very smart system of communicating with the whole plug material itself. In addition, it means that we have total control over the initiation process. So, for example, if we wanted to sever a casing which is beyond the tubing we've already severed, we would deploy these cartridges into the well, and all these cartridges, when we want to talk to them, will talk to its neighbour and are only active when we deploy a wireline tool. So the wireline tool comes down after we've positioned all these materials in the right place. Once we start talking to the tools, each one is talking to its neighbour, and we can then activate the initiators at our command. Then once we've initiated the process, we can monitor as each of the RFIDs shut down and where they shut down, so that we can monitor, log the thermite process in real time. Now, the next process I'm going to talk about is particularly what we're using in this might not be acceptable in some parts of the world, but we're working on this process in the Far East, and we're basically going to launch our cartridges from surface and using gravity as our means of deploying the additives into the wellbore. Now, this will enable us to have much faster feeding of materials into the wellbore. All the materials can be turned on only when we require. Obviously, the well is drifted before we install these. There's a large clearance for our darts to be dropped, and the darts are again multifunctional. And finally, we've built a test facility in Thailand, and we've drilled 3 test wells, and we're going to be doing in these test wells severing and sealing of tubing, severing and sealing of nested casing, and finally demonstrating that we can sever the riser. This is all going to happen hopefully just before Christmas. That basically completes what I was going to describe, and I'll hand it back to Henry.
Thank you very much, Phil. Okay, thanks to all our presenters. We've had a few questions coming in as you guys were talking, so I'm going to read a few of them out. So the first one is to Paul, and the question is, what is the melting temperature of the bismuth?
Pure bismuth melts at 270 degrees C, but what we do is we mix the pure bismuth with different metals to create an alloy. So our melting temperatures of alloys range from less than 100 degrees C all the way up to 260 and beyond. So depending on what the well temperature is, we choose the relevant alloy for that well.
Great. And obviously the thermite reaction creates a great deal of heat. Is there any danger of it damaging the casing?
Not in our standard tools. As you saw on the video, it's contained in a metal pipe, and that metal pipe contains the thermite, so the thermite never actually gets exposed to the well bore. It's just a heater. We are looking at using thermite for actually severing the casing, a bit like Panda. We're doing it slightly different. We're using a liquid thermite, but the intention there is to damage the casing, is to sever it or basically remove the need to section mill. But in most of the bismuth tools, obviously there's no damage to the wellbore at all.
Okay, and does the same apply to the production tubing? So is there any way that you might be able to get around the need for removing the production tubing from the well?
Yes, I didn't present it today, but using our new liquid thermite technology, which is just pumpable downhole and then settles, and then we can ignite it. We could remove production tubing, casing, basically any length you want, and we can do that very quickly indeed.
Fantastic. Okay, and a question for Phil now. How do the RFID work, and where do they sort of fit into the overall system?
Well, the RFIDs are a nice passive sensor that basically allows us to talk at a very low cost, and it allows each of these cartridges to talk to one another and allows us to have a controlled way of initiating the thermite reaction when we want to initiate the thermite reaction. We have to deploy a wireline tool which only talks to the RFIDs which have been deployed, and so the RFIDs are totally safe until we actually want to talk to them. And in addition to that, they could also include sensors or other type of reasonable cost technology that allows us to make the operation more intelligent and smarter.
Understood, thanks. And I believe you mentioned at one point the possibility of having a steel plug. How would that be possible using thermite?
Well, actually, the steel is part of the thermite composition. So what happens is when the thermite ignites, it actually separates out steel and slag. So we end up having, for example, if we have about 15 kilograms of base product, 10 kilograms of it will be steel and 5 kilograms of it will be slag. And part of the benefit of doing a uniform ignition process or distributed ignition of the thermite is that we heat up the whole material so the slag will float to the top and we get a long plug. So the steel plug could be 100, 200 feet long, depending on how much thermite we're deploying.
Fantastic. Okay. Another question for Paul here. Is the BISN plug an approved barrier by BSEE in the Gulf of Mexico?
No, our experiences with the regulators, whether it's BSEE in the Gulf of Mexico, the PSA in Norway, or the UK Oil and Gas Authority in the UK, is that they don't actually approve. It's more of they allow it to run. They don't stop you from running it. The obligation always falls back onto the operator, so it's the operator that makes the final decision. They just give it a blessing of approval. We've had blessings of approval to run this technology in the Gulf of Mexico, in the UK, in Norway, in the Far East, and down in Australia.
Great, thanks. And this is a question for both. We'll start with Paul. So is there a well deviation limitation to deploy your technology?
Yes, there is. I've just answered that question online. Yes, at the moment, we can only do up to about 82 degrees deviation. After that, because of the density of the alloy, obviously, it would run along the wellbore and it would create, the tool would have to be too long to create seal. But we are currently working with one of the major operators on a horizontal, truly horizontal version of our tool, which we would expect to be out next year.
Great, okay. And same question to Phil.
We haven't actually investigated this yet, but I guess it comes down to how creative we could be in terms of containing the heavy material in a horizontal well. But yeah, we haven't got a solution for that at the moment.
Great, okay. And so other than the technical aspects, which is kind of what we've been focusing on so far, do you have any idea of the cost differences between using your system as opposed to a cement plug? That's to Phil.
This will be a bit of a compare. I would imagine we're very competitive. I mean, the difference here is we are, well, it's very hard to circulate cement into multi-annuli and have a guaranteed seal because of stringing, etc. So with the fact that we can eliminate material to get a guaranteed solid plug provides you then with a solid barrier. So it's very hard to compare. We're not actually comparing like for likes. If you're saying how much if it's just the tubing alone, then typically the cement will be displaced by bullheading, for example, and then they'd have to hopefully rely on a plug to displace a large quantity of cement. I'd imagine we're very comparable in price. But then multi-annulars, I think, we're becoming a significantly more advantageous because we can get a guaranteed solid seal, which is not necessarily the case riglessly with cement.
Understood. Okay, thank you. And same question to Paul.
Yeah, it's an interesting question. How much does it cost to go back and repair a cement plug 2 or 3 years later when it's leaking, deep in the Gulf of Mexico or in the North Sea? So what we try to do is we do reduce costs up front. We reduce rig time. You don't have to wait hours and hours for our alloy to set up before you can gas test, which obviously helps on the cost. As we're increasing our production of these tools as well, the actual cost of the tool is reducing. But the main benefit to operators is being able to sleep at night knowing that they've done a good seal and they don't have to go back, because it's so expensive to go back and try and repair one of these wells.
Indeed. Okay. A question to Richard about your test facility. Obviously, regulatory approval is a very important part of using any new barrier material. To what extent have you or can you engage with regulators to get these technologies qualified?
So again, just coming back to what Paul said earlier, I mean, actually, the regulator has no regulations on this. Actually, most of it comes down to guidelines and making sure that the seal is adequate. And I guess particularly from the operator's point of view is being able to prove that the seal you can provide with an alternative technology is going to be as good as 100 feet of good cement. So a lot of this comes down to being able to show that the barrier you're going to put in will hold the pressure you've stated will do, that it isn't porous, that it's not going to corrode, and so on. So a lot of this, the regulations don't cover all of that. They say you have to, as an operator, you have to do a correct job and plug your wells well. So a lot of this will come down to looking at things like Oil and Gas UK's guidelines. And the last year's guidelines, I think, came out have a lot more detail about the qualification of alternative materials, certainly for the UK sector. So we'd be looking to look at those guidelines and see, as we work with developers and operators, how we meet those guidelines to try and qualify some of these materials, if that helps.
Yes, very much. And a follow-up question. So when will the testing plant be available to the market? Okay,
so big question. So that really depends on funding. So we have partial funding at the moment for the chamber. We will be going out to speak to industry fairly shortly. We will need some industry funding for this to back it up. We have some government funding at the moment, probably about 50%, but we will need some industry funding to put this in. So we're hoping to speak to a variety of operators later this year, well, what's left of this year, to see how we take that forward. So we look at various business models, how this would work. And obviously there's a mixture of things. It's going to be partly the operators, but also a lot of people who may be interested, actually developers. And developers may not at this point be able to assist in terms of setup of the system, but we're hoping we'll be able to get some sort of consortium between the industry operators and the developers to cover the leftover requirements in terms of cash. In terms of it's probably going to take us about a year to get built once we've got that funding in place.
Got it. Thank you. So question for Phil now. Is the PandaSeal technology commercialized in the US?
No, not at the moment. We're just getting very close to the completing our trials in Thailand, and then once we've completed our trials there, we'll be in a position to move to the US.
Great, thanks. And do you have a rough idea of timescales on that?
We should be completing our goal is to complete our trials by the end of this year in Thailand, and then do field trials Q1 next year.
Great, thank you. So this is a question for Phil and Paul. Phil, we'll start with you. Do you see your technology as being mainly there to complement a cement plug or to replace it entirely?
I think once the technology gets established, I think it could replace cement entirely, because cement's an old material that's often it's been approved, but it's unless you use vast quantities of it, you can never really be certain it will do the job properly because of the fact that the channeling and all the potential leak paths that end up being there. I think once we establish a solid metal plug, it'd be very hard to go back to cement, I believe.
Right, indeed. And same question to you, Paul.
Well, I think it's always good to probably have two different types of seal in a well. I don't think we're going to replace cement forever in every well. As you know, there's other technologies out there as well with resins and things like Sanderband, etc. And I think they've all got the place. We've got our place where it's very difficult to create a seal. We complement cement very well. We'd love to be able to say that one day we will replace cement in every well. I just don't think that's going to be the case. But we are definitely a big improvement to use for a gas-tight long-term seal compared with cement.
Understood. Thanks. Okay, there's a question here about thermite barriers. So the nuclear industry have tried and failed with this use of thermite barriers. How confident are you that the oil and gas industry can succeed where they failed? That's to Paul.
Well, we don't use thermite to create a barrier. We're using bismuth alloys to create a barrier. We might use thermite to remove casing so we can replace a barrier. In our experience, it's very difficult to create a gas-tight seal using thermite. And if you think of the end products of thermite is iron oxide and aluminium powder, iron and aluminium oxide. How long will that iron last? The objective for Norway is 3,000 years. If you're creating it with iron, we don't believe that will last the 3,000 years. So I'd say we use alloys as the barrier, not thermite. The thermite is just a means to melt the alloy.
Got it. Okay. And Phil, same question to you.
Yeah, we have the same philosophy actually, although we do incorporate some metal material into the thermite to provide a steel. We also use bismuth as our main sealing material.
Right, understood. Okay. And to Phil again, how can you guard against microannulus and similar placement issues?
The good thing about using bismuth is that it will migrate or leak into any microannulus because it's got such a low viscosity. So primarily we use the benefit of the bismuth to seal any microfractures that are generated by the thermite process or that exist prior to the thermite reaction. So the bismuth is a perfect sealing material for those microannuli, micro fissures, or very, very small flow paths because it will migrate everywhere while it's still liquid and then form a solid steel, or sorry, not a steel, but a solid material, a solid barrier.
Okay, great. And same question to Paul.
Sorry, I was just replying to some of the questions online there. Do you want to just repeat the question?
Sure. It's how can you guard against microannuli and similar placement issues?
So, as I mentioned earlier with the bismuth alloy, it's got a density of an SG of 10. So it's 10 times denser than a well-bore fluids and a viscosity of water. So when it's in liquid form, it'll run into the smallest of microannuli. We don't have to squeeze it. It'll just run there naturally. As it gets away from the heat source, it will then solidify and expand on solidification. So we don't have any issues at all with microannuli. We actually tackle microannuli with our technology.
Okay. And have you noticed any shrinking issues of the plug once the temperature cools down?
We haven't. We're actually testing now down to 4 degrees C. And that's been done successfully in some of the large plugs. As I say, the alloy actually expands on solidification rather than shrinks. So we don't have any issues with shrinkage.
Right, and same question to Phil.
Again, I think Paul just answered the question how I would answer it. To be honest, we have no problem at all with the microannuli.
And how about the? Have you seen any shrinkage effects on the plug as the temperature reduces?
We haven't done enough testing, to be very honest, to answer that question.
Okay.
I mean, we do basically, because of the material characteristics of bismuth alloys and steel, you do get some shrinkage, but we still pass the successful gas test.
Right. So here's a tricky question for you. Since P&A is for all eternity, is there any way you can simulate the effects of time on the plug over very large timescales?
I'll jump in on that one. We've got a big program, as I mentioned, with the Oil and Gas Technology Centre in Aberdeen. We've been working on it now for about 18 months. Part of that program to see how long the alloy will last. We're getting very favourable results. We're also developing a model so we can simulate for long periods of time how long the alloy and the plug will last. Can we guarantee it's going to last 3,000 years? No, we can't. I think you'd have to say I was crazy if I could guarantee that. Can we do a better job than cement? Yes, I believe we can do.
Okay, I'm just going to jump back in now. Obviously, a huge thank you to all of our panelists and everyone for tuning in as well. We are out of time, unfortunately, and so yeah, we're going to have to wrap it up. But as I say, yeah, massive thanks to Paul, Phil, and Richard as well, and also to Henry as well for kind of chairing the discussion. I apologise to anyone we didn't manage to get to your questions, but yeah, as I say, we'll have to wrap it up now. Henry will be with us in Decon World 2020 next year with a PACE panel. Richard's going to be involved with our R&D zone, and we're also looking to see Paul and Phil at the event as well. So, you know, all of these discussions and much more will be happening on the 31st of March and the 1st of April next year in Houston. So, yeah, we'll wrap it up there. But thanks for tuning in, and hope to meet some of you next year.
Thanks very much.
Thank you.
Thank you, everyone.